Okay, today we want to continue our study of engines and pistons by looking at energy flow and the signs of that energy flow. So we've already talked about work. I just want to refresh your memory because this is a tough and important idea that with your piston, work is going into the gas when you're compressing the piston, and work is coming out of the gas when your piston is expanding to a bigger and bigger volume. The amount of work we saw was equal to the pressure times the change in volume. Important equation we're going to be utilizing very soon. I want to show you an example. This is one of those things that I wish I could show you in person, and it is on my list of things to show you once we're back, hopefully in the early spring, if not even sooner. Okay, this is what's called a fire syringe. It is a cylinder with a piston that is airtight, and you compress the piston really quickly. Inside the fire syringe, all you have is air and a small piece of paper, usually very thin, almost like tissue paper. And what happens is, when you compress the air inside, it causes the air to get hotter, hot enough that it actually lights the paper on fire. So you are literally burning the paper using work, okay? So here it is in super slow motion, super zoomed in. Hopefully you can see this big bright flame as the paper ignites. The temperature has gotten so hot that the paper spontaneously ignites. We see the same type of thing inside of our car engine during phase 2 when we are compressing the gas. Here's how you want to think about it. As the piston moves up, it's pushing on the air. That makes the air speed up. The piston is pushing the air particles, and that push accelerates them to a greater and greater speed. These particles are now going to be moving very, very quickly, which means the temperature is going to get very high. Okay? So, work going into the gas. I want to revisit. What is happening again is the piston is moving down. As it moves down, it collides with these molecules. It gives a force to those molecules. It accelerates those molecules. Those molecules move faster, and that means the temperature goes up. Okay? So the piston pushes the molecules, speeding them up, making the temperature get higher. If we do this fast enough, we can get the particles moving so fast that we can make things ignite. Work coming out of the gas is just the reverse. That's when the molecules themselves push the piston up. As they push the piston up, they give some of their energy to the piston. So the piston rises as the particles lose energy and cool off. Realize that's not the only way we could heat up the air. We could heat up the air in a simpler way, which we call heat, which you've learned about before. So the way to get heat to go into the gas is not to move the piston, but to have the outside hot and the inside cold, and then the heat will just transfer right through the walls of the cylinder. Okay? So this is our second way of getting energy to these molecules. It's called heat energy. And it's the energy that happens because of a difference in temperature. The heat always flows from hot to cold. To get the heat to come out of the gas, we just reverse it. We make it hot inside, cold outside, and now heat will pass through the walls to the environment from our system. Okay, and we will have heat escape from our system. So there are two ways to get these molecules to speed up. There are two ways to make the temperature rise inside the container. One of them was obvious from the past, and that is called heat, which we just talked about. The other one we just learned about. This is when the piston causes the molecules to speed up, and that's called work. With work, we are adding the energy in an organized fashion. We are pushing down on the piston, and it is moving in a single direction. With heat, it is just the random motion of the molecules transferring energy from the outside to the inside through the walls of the container. Either way, they are doing the exact same job, and that job is to increase the kinetic energy of all the molecules inside the container. That can be written as delta U, change in internal energy, or it could be written as delta KE, the change in the kinetic energy of those molecules inside the container. This is more standard. This, I think, is more understandable. Okay, so we have work, heat, change in energy, and they are all measurements of energy, all measured in joules. Okay, so here's your energy flow. We could have work go in, we could have heat go in. Both will cause a change in kinetic energy. Okay, I'd like you guys to be able to figure out what is the change in kinetic energy. So most times with pistons, both things are happening. We have work going in, we have heat coming out. We have heat going in, we have work going in. Could be all kinds of different combinations. You got to figure out how much the energy inside changes. Okay? So I'm going to have you guys try working through these, and then we'll see how you make out. 20 joules in, 3 joules out. 20 joules in, 3 joules in. 3 joules in, 20 kilojoules out. All right, so what is the change? Hopefully you see with this one, we have a change of 17 kilojoules positive. 17 more went in than came out. With this one, we have a change of 23 kilojoules positive. And with this one, we have a change of negative 17 kilojoules. Make sure you understand these. Okay? 3 went in, 20 came out, we lost 17. Okay, here it's a little bit harder. I tell you the change, I tell you the work, you find out how much heat went in. Okay, hopefully you see this must be 30. 30 went in, 25 came out, that's a change of 5. Here, 20 went in, 25 came out, so we lost 5. Here, we lose 10, so we must have only had 5 go in. Okay, this time we have a few more. I don't even show you the arrows. You got to figure out what happened with the heat. Five went in. 7 more went in. So that gives us a change of 12. Here we have a change in 2, positive. So 27 must have gone in. And finally, 20 went in, which means 20 must have come out because we have a change of 0. All right? So these are just logic problems. You got to look at what came in, what came out, and determine how much the internal energy changed by. Here we have work, so I'm not telling you if it came in or when it came out. So take a look. You lost a total of 10. So 13 must have come out. Here you gained 10. So we're going to need an extra 7. 7 went in, 3 went in, gave me a total of 10. Okay, here we gained 10. So we must have had 18 go in and 8 come out. to give a change of 10. Okay, I just want to make sure you're clear on the signs. So heat is positive when the heat enters. That happens when the temperature is hot on the outside. Heat is negative if it leaves my system, meaning it's cold on the outside compared to the inside. And heat is 0 if no heat enters or leaves. This could be because the outside and inside are at the same temperature, or the piston might move so quick that the heat has no time to escape. Okay, so that would be for 0. The process happens really quick. The temperatures on both sides of the piston are the same, or the piston is very well insulated and does not allow heat to escape. Work we saw was positive when we compress, negative when we expand, and it will be 0 if we do not change the volume. Okay, if the change in volume is 0, no work gets in or gets out. Change in kinetic energy is positive if the temperature goes up. It's negative if the temperature goes down. And it's 0 if the temperature does not change. So I know this was a lot, but I hope as you go through this and the Google form, it starts to make some sense.